module today, we will be discussing mostly about how LLMs came into being, why the current structure is important, and accordingly, we will move ahead to the next. So you can see that we have these two aspects in the crash course content, the day one and day two. So today we'll be focusing on the day one. I will be talking about this in more details as more students join and we start the course at that, like start discussing. I hope all of you guys have joined the previous meets on deep learning. Uh, Lucky, Mrityunjoy, Rupali, and Riti and Rohini. All of you have joined the past meets. I hope you're aware of the deep learning aspects, right? Can you say yes in the comment box, please? Or no? You can type also. Accordingly, I will change my pace and adjust my pace of teaching based on your. Okay. So Lucky Riti has have joined. Okay, Rupali has joined and learned back propagation. Okay. What about others? Ongana, Rohini, um, Mrityunjoy, Konishko. Did you join last meets? So, what are your background, guys? Like mathematics, economics, computer science, electrical engineering, mechanical engineering. What is your background? So, I will ask the students since there are less number of students, so it will be great to get to know each other. So, Angana, what is your background? Okay, Lucky is computer science, Riti is electronics, Mrityunjoy, Rohini, Rupali. Okay, Rupali is computer science.
So mine also computer science.
Okay, great. Shurojit, great. So, most of you are computer science. Okay, Mrityunjoy is information technology. So, in your course, so are you all under NEP or like, okay, Shurojit also information technology. So, you are in NEP 2020 or you are outside NEP 2020? Like, do they have 4 years? No, okay, you are all BTech, so of course it's 4 years. That's natural. So, how is the syllabus in computer science right now? Yeah, did they include like deep learning into the whole thing, or uh, how is it? Did it develop from the previous years, guys, or in IT or in electronics? Is it any different? Okay, so like you said that MLDL is also included. Okay, in computer science, that's great. So they're teaching. Yeah, in fact, I'm not sure who will give GATE DSAI. I'm sure. Okay, there is basics of AI in BSc level. That's great. But I hope quite a few of you will get data science and AI for your MTech probably. I don't know, or in the future job. So in Get DSI course actually includes quite deep fundamentals of data science, machine learning, and deep learning. I really like the problems out there. So all the best for your preparation there. Okay, I think we can start. CSI, is it good to start because it's already 5 minutes? or will I wait for some more time?
Yes, sir, you can start.
So hi guys, I'm Srijit Mukherjee. Very happy to have all of you here. Even though there are less number of people, that's great because I will be able to make sure that all of you understand and accordingly teach you. So it's a super important thing. So that when you get out of this 2 hours of interaction with me, you feel aha, that was fun because you learned something new. So today I will be before I move ahead to the whole course, what I have planned for you for today and the next day, to on 5th of August and 23rd of August, I must make sure that uh, you know that you are on board with the fundamentals that is needed. So I will assume that the prerequisite for this is what you have already done in the previous sessions, like mostly deep learning. However, I will review it for your own. For I will review it, revise it, okay, so that uh, you can just reconnect the dots backward. And to introduce myself, I am Srijit Mukherjee. I have done my undergrad and graduate studies in statistics from ISI Calcutta, rather Kolkata, and also I'm currently pursuing my PhD in AI, in applied AI in medical sciences, mostly in brain imaging, in Penn State University. And during this time of moving from master's graduate studies to PhD studies, I have also been involved in building in my entrepreneurship ventures, like EduTech company. Like I don't know if you have known Chinta, so where I teach statistics and data science to students. So and this is all being done out of my passion and love for the subject, for data science and statistics and machine learning. And I hope I can transfer and I can share my passion with you, and you can also get inspired and love to learn more after discussing with me. And as I said, um, it's a small group today, and I am so excited because um, I will be able to interact with individual each one of you. And I really want you to use this opportunity to interact with me. And you can use your voice, unmute yourself, and comments to discuss with me and ask your doubts. Stop me anywhere you want, ask me wherever you want to. Didn't understand. It's a 2 hour long content. So we need some constant discussion so that you don't fall asleep and I don't fall asleep. It means our minds don't fall asleep. So we all know about the importance of large language model. Okay, we have been seeing the whole beauty and hype together of large language model. And this course that I have developed aims to unravel the mystery, if you call it, or unravel like what's happening under the hood, what's really so much um, life changing or tech changing. So I have divided this course into two halves. One half is building the foundation. It's mostly mathematical and core basic foundation of LLM. And the second day, I will be doing some hands-on where I will not really code from scratch, but I will show you codes at how it works and actually build an LLM from scratch. Okay. So today's lecture, today's underst- today's discussion and interaction will involve three core components. One is the problem statement, as you can see here. So by the problem statement, I mean, so let me just adjust it so that I can start writing. So problem statement is that what exactly we are trying to achieve by large language models. Okay, what is our goal? What is the problem statement? Um, there are multiple problem statements, but what exactly is GPT doing? And once if we like to solve a problem, we need to know the problem statement first, right? Then only we can solve. And then we will see that a vast, a major component of that problem statement is understanding language, understanding the mathematics of language. And we will understand the mathematics of language. And I believe today's most important, fundamental ideas of the mathematics of like today's fundamental ideas lies in the second section, that the mathematics of language. And you will, the most of the value you will get is out of this. And then we'll discuss about the deep learning process, okay? That how the whole thing is developed step by step, and how we can use and take this mathematics of language and inject into the deep learning process based on what you've already learned. I will not assume future knowledge. I will assume only past knowledge of yours. So this is all I have to offer today. So let's get started. Okay. So any questions from your end? I hope not, because we have not started yet. So let's first go to what is the problem statement that we are trying to solve. So you've all used GPT for sure, right? So if you all use GPT, there are two things, there are two components to it. One is the input and one is the output. So you ask a question that help me study vocabulary, write a sentence for me to fill in the blanks, and I will try to pick the correct option. Okay. So let's say this is the input, and you get an output from the GPT. Let's say a text which says absolutely, let's start and dot 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 dot. So that's the whole idea of GPT. So there's an input and there's an output. Okay. So what exactly is the problem statement that we're trying to solve? So there's an input X and there's an output Y. Okay. So let's understand it in more depth. So the problem statement is this simple. So you already learned the deep learning. Now I will start connecting the dots backward, as I said. So let's zoom it in. So this was the first input. The input is this text that helped me study vocabulary. So it's X. And now this LLM is nothing but this huge neural network, which can be mathematically represented by a function X. Okay. And the input, sorry, the function F, the input X, and then some unknown knobs and parameters, okay, theta. And we will see the importance of these knobs and parameters. You've already seen in MLP what you have done in deep learning, but these knobs and parameters make it better. Now, what is it? What does it make it better? We will define it later on when we revise the deep learning process. But essentially, you can see these knobs and parameters make it better to have a better output. Okay. So it has an output Y. So we will use this notations X and Y repeatedly, okay, over and over again. And this is some unknown parameters, and the whole problem statement is to find the best parameters so that given an input, the output is better. Okay. Now the main issue is this is still text. As you have seen, this is still text. So we have to know the mathematics of this text to understand it. So the first basic mathematics is that the first basic mathematical representation is this, that this text, if you observe very carefully, very minutely with attention, that you will see this text is nothing but you can say that it's X1. Let me just reduce the. So you can see that this is X1, the help is X1, then me is X2, okay, then study is X3. So it's a sequence of words, you can say. So I can call it as of now a sequence of words. So I represent this as some X1 and X as a tuple, a list of X1, X2, dot, 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 Xn. Okay. All of you are on board with this, guys? And similarly, the output is X1, X2, and Xn. Can you give a thumbs up or write yes in the comment box or boom in the comment box? Anything works. Did you understand this? That it's a tuple. You can represent it as a tuple. This is one checkpoint of concept. All of you got this, guys? Can you say yes or no? Okay. Okay. So 4 students said, what about others? Less number of people are here, so I want to hear everyone. That's important. If you do not want to interact with me, please don't attend the class, okay? That doesn't make sense. It's a both by path. So I actually call out all of your name. So Angana, Konishko, because I want to make sure you understand and do not waste your 2 hours. Konishko, Lucky, Mrityunjay, Rohini, Rupoli, Sanjana, Shupriyo, Shurojit, and Ritik. All of you understood this, guys? So 4 people have said yes. What about others?
Yes, sir.
Okay. Thanks, Shurojit. Angana, thanks. What about others? You can also give a thumbs up if you want. Okay. Okay. Okay, great. So I've got most of your answers. So yeah, please keep on interacting. This is very important for me, okay? Because I want to make sure that you understand by the end of the 2 hours. Okay, So let's define this a bit more in depth. So what we have discussed here, that an input and output both is nothing but a sequence of words, let's say, we can say. It can also be represent a sequence of characters. So if you say H is a character, okay, it can also represent a sequence of characters. And you will see that this sequence has some special meaning. So the sequence is what makes it happen. Okay. So what is the perfect, what is the optimum sequence to take? Okay. What is the optimum sequence to take? That's what is called, is the fundamental of tokenization. And we will talk about it in details. You know, the interesting part about language is that language is text, and we want to convert into a proper mathematical basis. Okay. We want to build the foundation of the mathematical foundation of what is language. Unlike image, you know, in an image, if you observe in an image, probably you have learned computer vision or a signal, it's easy because, you know, each pixel has some mathematical representation to it. That's how it's built. When you click a picture, that's how it's built, by intensities in each pixels, right? Each pixel constitutes an intensity. But in language, that is not present. So that's why we will spend, as I said, we will spend a large part of our time in understanding mathematics of language. And this is the first step, that a language is nothing but a sequence of something. We can say sequence of words, we can say sequence of characters, and we will actually converge to this point that a text is nothing but a sequence of tokens. And how these tokens play a very, very, very fundamental role in LLMs. Okay. So okay, let's revise this basic stuff. So as I said, that given a text X, you want to define some X1, X2, Xn, as you can see. And we will again do this in tokenization, but here are some examples. As I've already said, that X can be a sequence of word-wise. Like, let's say this text is, I love large language models. And you can say that each can be each word, love, large language models. And in fact, this full stop is also a word. And similarly, you can do it by character. You can do it by I, L, O, V, dot, 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 right? So this can be character-wise too. So the question is that can there be other ways that increases your understanding? And if yes, then what are those? What are those ways? So as I said, I will repeat once again that if you, let's say, it's like, I will say this large language model is kind of very much like stock price prediction. Okay, let's say you have hundreds days of S&P 500 stock data, and you want to predict the next 5 days. Similarly, you have the text of last 100 tokens or words, and you want to predict the next 5 text or 100 text. You see, it's a similar kind of thing. And we have to make sure, because when we take the example of stock market, we will actually, our understanding will become more clear of how to design the deep learning training process. We will come to that again. Okay. For example, to give you a heads up, for example, we will never train a stock market on future data, right? Similarly, we have a large text, we will never train on future data, like in the sense that we will never take it as a training data set, right? So this is important for you to understand. But yeah, so one important thing to understand is that stock market is more random, okay? And that's why it's hard to predict. But language is not random. We have an inherent structure. That's why we can speak language, because we have an inherent structure to it. And that's why our mind cannot predict stock market really easily. But we can speak really eloquent language. We have good verbal skills. Human beings have good verbal skills. So that's why, because it's not hard, but it's an easier problem. So again, revising the problem statement. So now, if you, as I said, I will revise this whole idea of where this theta is important. So now we have this set of, now what we will do is that the deep learning process is this, that given a pair of xi and yi, that what is the input and what is the output, we have these pairs, right? xi, yi, x2, yi, sorry, x1, y1, x2, y2, dot, 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 xn, yn. We want to find that best parameters theta, those knobs, such that the prediction that is f of xi comma theta is as close to the ground truth y's, the yi's. Got it, guys? All of you on board with this? You have already learned deep learning a bit. So, do you understand this? All good? So, given this xi, yi, this x1, comma x2, y2, x2, comma y2, dot, dot, xn, comma yn, how do we find these best parameters of this large, super large neural network that can help you make the prediction f of xi, comma theta? This theta, as you change the theta, this prediction also changes. So which theta is the best so that the f of xi comma theta is as close as yi? All of you are on board with this, guys? Did you understand? Can you say yes, no, ask me doubts? Okay?
Yes, sir.
Super. What about others? Anyone who didn't understand and you want me to tell you and teach you once again? Okay? Okay, Mrityunjoy, are you understanding? Shanjana, Gargi, I saw that Gargi joined late, so are you understanding?
Yes, sir.
Good. Okay. Okay. So now our first module is over. That is the math, the problem statement. What is a problem statement? To revise in one word, we have this text, which is a sequence of tokens, sequence of words or characters. We don't know what it is. We will discover it today. And you want to predict, again, a sequence of tokens. And we have to accordingly design, as I said, the design that what are these xi and yi. So you will be given a big text, right? A big text. Let's say you take a whole book, okay? A book. And the question is that based on this book, how will we design this xi and yi? We will come to the end, towards the end, what these are. This is unlike any other image problems, like in dog versus cat classification, okay? Let's say you want to classify between these two things, okay? So what will you do? You will take pictures of this, similar things. You will have, let's say, 100 pictures, and you will have 100 pictures of this. And you know this is a label. So you know the xi is the picture of different dolls, and xi are also pictures of these different apples. And you have the yi, which are the labels of this doll, and let's say, or and an apple, right? And accordingly, based on this, you train the model. So we have well-defined xi and yi. But in language or stock market prediction, we don't have this well-defined xi and yi. We have a large text, okay? So we have a Wikipedia page. So the question is that, this is a very fundamental question that we should answer. And this is very different, important, is that how do we, so let me add a page of important questions, because these are the questions that you will live yourself with for a few. So I will tell you the ideas, but I am putting the seed of idea inside your mind, and that seed will go into a tree in the next few years while you become a machine learning person or data scientist, okay? So important questions to think about in details. Number one is that we have a large text. The question is that how do we divide them into xi and yi, like input and output pairs. And second important thing is that, if I take an image of this toy and I take another image like this, or maybe I take two images of two different toys, okay? Let's say these are two toys, and these are independent. You see that x1, y1 is independent of x2, y2. But in time series or stock, it's the same thing. It's a one-dimensional or one-dimensional objects. But in language or stock or time series, let's say, which is dependent on time, are not independent. Let's say I speak something. Now, I speak is dependent on speak something. If you consider this two is different, I speak something, and this I speak is dependent on speak something. So are dependent on each other. These are very important distinction, okay? And this seed of thought should stay in your mind while you build your future models after 3 or 4 years. For your company, for your research, for your own, let's say, entrepreneurship journey, whatever you do. But this is very important. You design a training process, an evaluation process. Okay, these are fundamental questions, and these are very important for you to think. Okay, so now comes the second part. So we are done with the first part, the problem statement. Okay, now we have understood that language as a data is very, very diverse and different from images data that you will be learning in the future, like convolutional neural networks class, right? Or you will probably learn RNN and LSTM. So RNN and LSTM are meant for this kind of time series data. We will not do that, and we will actually discuss later on in this slide. I will show you that why RNN and LSTM cannot solve this problem of large language models. We will come to this, okay? But that's a suspense for you. Okay, so now we are going to the next part, that is the mathematics of it, the mathematics of language, the structure of language. Okay. So all of you are good with the problem statement, guys? The problem statement is clear in your mind? All good? Can you say yes? Or no, if you didn't? Understood? Yeah. Emoji is fine, perfect. Yes, like that. Hands up is also fine. Like this. There's an emoji button out there. Okay. Okay. So now the next part. That tensors, thank you all of you for the response. The tensors are the fundamental math of data. Tensors are how computers store information. What is an example of vector? What is a tensor? Therefore, let me define what is a tensor. A tensor is a vector or a matrix or a generalization of that. You can say tensor is like a n-dimensional matrix. Okay. So I just gave a generalization, or you can say it's a vector, multi-dimensional vector, but the n-dimensional matrix makes sense. For example, an image is a tensor. This is let's say an image of Abraham. If you zoom out, you will probably see this is Abraham Lincoln. Okay. Former president of United States. And if you zoom in, and you will see that what does this pixel represent? That's an important question. And naturally, this pixel represents, each of the pixel represents the intensities. Okay, each of the pixel represents the intensity. And if you just remove the picture and just focus on the numbers, this is nothing but a matrix, right? So an image is inherently a matrix, and a matrix is a tensor. Now, if you take colored images that has 3 channels, one is a red, one is blue, and one is green, and that will become a 3-dimensional tensor. There is a red one, so there will be a red one, there will be a green one, and there will be a blue one. So I have to download the blue option. 3 channels. So it will become a 3-dimensional channel. Okay. And if you observe that this image will have this dimension of the tensor c, h, w, where c is the number of channels. If it is a colored image, it's the 3. There are other kind of images too. Many kind of image. Okay. So here in my research lab that I work on, the radar sensing image, the different kind of images. Okay. For example, there's a company called Dolby which looks at different kind of images. Okay, which just sees. Okay, so let's say you are a CCTV surveillance company, okay, or building CCTVs, and you want to store less amount of data because if I have a CCTV or a webcam, most of them doesn't don't change. The images don't change every frame by frame, right? So they're in a different kind of data storage methodology, so that they can store data well. So what they store is the first frame and how the frame is changing. If it's zero, they don't store it. Okay. So if it's large change, then they store it. That means what? The storage has reduced. So that needs a different kind of camera. Okay. So essentially, images are the natural mathematical representation, a tensor representation, what we call. The question is that language don't have it. Like, I love large language models. This has no mathematical representation. The only mathematical representation that we have discovered together right now is that it is a sequence of something, sequence of words. But what is a mathematical representation of a word? Okay. So if I ask you this simple question, that how can you represent, what does a word mathematically mean to you? So here's my open question to you. So we will discuss for next 30 minutes or 1 hour that what is a mathematical representation of language, but I want to have your insights. So what do you think a word is? How can you represent a word mathematically? So any ideas, guys? Any ideas? Angana, Gargi, Hindol, Konishko, Lucky, Mrityunjay, Rohini, Rupali, Shanjana, Surojit, and Riti. Any ideas that how will you represent a word? Like a math and data. Let's say they take these two words. So how do you mathematically represent this word? So what do you think? Any ideas, guys? Throw your ideas. Let's discuss. What do you think? How can anyone who wants to discuss with me or share his or her ideas, how can you represent a word mathematically? What comes to your mind? The number of characters, the length of the word. What do you think, guys? Any ideas?
So not
Yes.
just length, but I think there should be some kind of a logical interconnection between the first and the second character. And
Okay.
the constraint is that it should be present in the current language's vocabulary. Say A, B, C. So how are they connected? Interconnection between A and B and C. Does it make a sensible word in English?
Okay.
Not mathematics, but actually something like graph theory or
Okay.
networking.
A
The way
network of words. That's good.
a
So
network
maybe
of
it's
characters.
symbol or expressions.
Okay. Symbols, expressions. So can you explain a bit more, Gargi? Thank you, Rupali, first of all. Yeah. So can you explain a bit more, Gargi? What do you mean by symbols? So these are the ideas given by the students. I'm very happy. So what do you mean by symbols, Gargi? Can you unmute? I think you're on mute. Okay. So any other ideas, guys? So Rupal, you want to extend on this something, or other students have any
Yes,
ideas?
maybe
Actually,
we
it's a
can.
Yeah, go ahead, Gargi.
oh yeah. Actually, it's a symbol mean some sign. I mean operators.
I am not getting. Can you explain a bit more? Sorry.
Uh, Suppose some operators or symbol that is alpha, beta, plus, minus that type of symbols.
Okay.
Is it?
So okay. So what I'm saying is that there are two words. Let's say math, or let's say let's take this since two of your here. Let's say Gargi and Rupali. There is two words. Okay. So what are the mathematical representation of it? What do you think is a good mathematical representation? So Rupali already said some of her ideas. So Gargi is saying symbol. So can you let's say you take your name and use it as an example to explain your idea, Gargi. So are you talking about GARGI, this as a specific like individual symbols?
Maybe it's treated as
Uh,
symbol or total. What is the length of the? I mean, if we consider it's a string, that time we count the length of the string.
Okay,
Okay.
length is already
Uh,
mentioned. Very good.
yeah.
What else? Yes, Hindol.
So
Yes.
I have one point to say. we can also use the ASCII values of the characters that make the
Okay.
word.
So ASCII values is a good idea. That's a very good guess. Yes. What else? But it's like, let's say Hindol. Okay, Hindol is also now joining the list. Let's say if you combine the ASCII values, so ASCII values are nothing but each word has a specific string attached to it. Okay, you can call it 1, 2, 3, 4 like this. So Gargi will be represented as, let's say, 1, 5, 7, 6, 5. Am I right, Hindol? Like, yes.
According to what convention?
No, so it's like I'm just defining, let's say, in increasing alphabetical order, okay? I'm just giving an example. So I'm not like going into the depths of ASCII values. So what I'm saying is that each word will therefore contain a value, okay? A numerical, alphanumerical value, right? No, sorry, numerical value, right, Indol?
Yes, yes.
Yes. So now what I'm meaning is that now Gargi, Rupoli, Hindol, this will have different numerical values, right? That's a very good movement from words to numbers. That's good. That's really great. So we can add this ASCII values. But the question is that, does it really contain the meaning of Gargi, Rupoli, or Hindol? Or there is something more? So as they have said, length is important. So length can be captured by ASCII value, okay? So we can say the length is solved. And there's a logical graphical connection. And symbols is also solved that Gargi has mentioned. So ASCII value is a great extension. What about other ideas? What other? So we couldn't solve the symbolic meaning of it. Or is there any more meaning of it? What do you think, guys? Any other ideas to think about? Because this is the most fundamental thing that we're going to discuss today.
Sir, if putting B after A is syntactically or logically correct, then we can assign a good weight to between A and B. So like this, a word can be represented by weights of, say, G. After G, we have A in Gargi's name. So because Gargi is a correct word, so G can be related to A by a certain weight, which will not exist if I write GX. GXRGI is not a correct word. So maybe if I type G and then I type X, so that this will hold or carry less weight than if the word is GA. The sequence is GA. So the interconnections can also have a weight.
Yes, very good. So you will see all these things actually come up in what the solutions that people have mentioned. So I wanted to get it out of your minds to think that actually you can also do it. Okay, not these people who have done it, but it's actually you are doing it. But these people have generalized it and made it happen. So get your ideas moving, guys. This is the most important part. So yeah, very good idea. So interconnection actually holds a very important role. We will formalize it mathematically. So don't worry. But the ideas are important. What other ideas, guys? So Gargi, Hindol, Kanishko, Lucky, Mrityunjoy, Rohini, Rupoli, Shanjana, Shurojit, Riti. Any other ideas you have apart from this? So, there's one more idea that is missing, and I want someone to talk about it. Something more, something depth. Okay, I will give you a hint. Let's say, think in terms of, I will write 3 random words, and that is the hint of yours. So I will say apple, headphones, and banana. I hope reading I misspell banana, because nowadays I write with ChatGPT. Okay, so I have a misspelling thing. So please correct me if I'm wrong. Okay, let's say mango. So these are the 3 hint words to you. Now I am trying to convey some message to you via these 3 words, and that is what you're missing. Okay, so this both apple, headphone, and mango contains logical. Let's say you have built a logical expression, but there's something more that is there that you are not, that you also have to make sure that's happening. So think in terms of these three words. That let's say all the logic is there, but there's something more to it, something more to the logical connection between this apple, headphone, and mango. What is that? What is that something other relationship? Think in terms of what is the relationship between these words that we are not capturing using symbolic logic. Think
Are you
about some
talking about
relationship.
sequence
of
in which sequence we have to write these words?
No, let's say these three random words.
Okay.
Then what relationship we are not capturing? What relationship is there more than just symbolic expressions? The furthermore hint is that take relationships between them. So any ideas? I know you know. I just wanted to get it out of your system, out of your mind. So what relationship?
Yes, subject and predicate. Subject and predicate, something like that. Subject and predicate.
Not really, but think in these terms that if you take there are three pairs of it, right? Apple, mango, apple, headphone, headphone, mango. Okay. Now think in this term that is there a strong relationship between any of these pairs than the other? So let's say you have these three, apple, headphone, and mango. Let's say you build a connection between them, like a triangle. Now, can you like can you see that any of this connection is stronger in some way?
Yes, the apple headphone and apple mango is stronger than mango headphone.
So which one is stronger?
Apple headphone and apple mango. Apple mango because we can say they are fruits, and apple headphone we can associate with the company. Some context is needed, of course. Apple and headphone.
Great. So exactly, Rupali. Thank you so much. So okay, so okay, everyone should actually say thank you to Rupali. Can you say thank you? I mean, it's a really good idea. Okay, we are missing the idea of meaning. So there is a logical connection and there is a meaning connection. So there is a symbolic position-wise logical connection. So there's a positional connection or frequency, like how they are occurring together. Like for example, U always comes after Q, right? So there is some relationship between them. Like always as after a subject, after a subject, always a verb will come naturally, right? To say that the subject is doing something, like when the action is present. So there's some positional aspects that are naturally there. That's where the symbolic logical things come. But there's also another thing that is not present by logic. That is a meaning, right? Like apple and mango can be present at two very different parts of a whole text, but still they have a meaning, right? So they have a meaning that is beyond position, that is beyond logic, and beyond like symbolic symbols, right, guys? All of you got it, guys? Yes or no? These
Yes,
two things
yes.
are very. Yes, Hindal.
Yes. Got it.
Super. What about others? All of you got it? Thank you for your interaction.
So you mean that we are not just randomly putting them together, but the entire arrangement has a meaning?
Yeah. So let's say let's say you build up something, you predict some text, but you do not have the meaning. Let's say you want to generate a text. Okay, I want to eat the fruit. Okay, and you want the GP to generate it. You want it to tell both apple and mango, not just one. Okay, let's say text has more apples than mango. Naturally, the text will predict apple. But you want it to say mango, and for that you need the meaning of that apple and mango are not different with respect to the fruit. Make sense? So as you said, there's a fruit here. The connection is fruit, right? So this meaning is just not captured by the positional thing. That's what I'm saying. Am I making sense, guys? Did you understand, Rupali?
Yes, sir.
Position does not encode the meaning. Like just position just do not encode the meaning. There needs some meaningful, yeah. All of you understood? Is it clear, guys? So there are two things. One is the position and one is the meaning of words. So Angana, Gargi, Hindol, Lucky, Konishko, Mrityunjay, Rohini, Rupoli, Shanjana, Shurajit, and Shagato, and Riti. All clear, guys? Any questions? Any questions you have?
Yes, but what do you mean by position?
As Rupoli and Gargi have mentioned, that there's a relative position of as like if after I, am will come probably, right?
Okay.
So after a subject, and if there's an action, let's say I'm going to do an act. Yes, please. Sorry. Go ahead, Hindal.
Yes.
Yeah. So let's say there's an object and I'm a subject. I'm going to do some action with this object, right?
Okay.
So naturally, after that, I to go to do some action on this object needs some verb out there, right? That via which I will do the action. So that
Yes.
verb will always come between the object and the subject. I'm just telling in a brief, like in a simple manner. But this is what will be my symbolic reason between words. We can have symbolic reason between characters. Like you always come after Q in a word. Okay. And other things are there, like between consonants, vowels come, right? So that you can speak. So this naturally come up, and we are not hard coding it. We want the machine to learn by itself. So that's why I'm saying that we have to understand the language. And this is so what I think that there are multiple ideas that you shared, but two of them, like if you want to cluster them together into two groups, one is about the meaning and one is about the position, and they're orthogonal in each other. They are not like related to each other. Like they're related, but position just cannot always like tell us meaning. Okay, did you understand?
Yes. Understood.
But sir, I think position is what the sequence is what actually gives meaning to what we are saying.
Yes. So okay. So you're right. For example, I want to eat apple, and I want to eat mango. Okay. So if you have these two sentences, Rupali, and if you train, they will understand that there is a relationship between apple and mango, that they are together, that they mean something together. That's what I mean by meaning. Okay, make sense? They have the same meaning, that of food. That's what I mean by meaning. Yes, of course, it will be discovered by position only. But what I'm saying is that this eat an apple position is different from apple and mango like meaning. So this is what I call by meaning. This is what I call by position. After eat, some food will come, but that food can have options of apple and mango.
Yes, so I understand. It is like a placeholder. Instead of apple, mango, we can put any other, but it should be
yes. So that's what I mean by meaning. And when you say, yeah, so there's no meaning when you say eat an apple, because as you said, Rupali, you're right. But yeah, this is important, and these two are distinct things. Of course, this will be described by the relationships and the positions of different words and characters, but both are orthogonal in nature. Both are different in nature, what we understand. As you said, placeholders. Yeah. All of you got it, guys? Okay.
Yes,
So
sir.
now, going to the next aspect. Let's mathematics. So what you have done is what I have said is absolutely perfect. And now we will be formalizing it. So the formalizing it is the following. So there are two different things. One is called the statistical semantics and distributional semantics. So statistical semantics is nothing but the positional thing that you have said. See, you have only said, I have not helped you in anything, right? Of course, I have helped you, but you are the people who have actually discovered it. So there's positional connection and there is meaning connection. The statistical semantics is nothing but these are the prerequisite words that have been done before deep learning era, are nothing but the position. This you can see these are like how many times these words have occurred together. Hospital and med tech occurred together. Here is something. Let's see what I cannot even. Yeah, crime and prison occur together. Do you see the point? They occur nearby. They occur together in the same words. So you can say that you can take sentences and see which two pairs always how many times it occurs. If they're occurring more and more same time, that means they're together. So this is nothing but the positional encoding, the positional relationship. But there's also an extension of like distributional semantics. Okay, that is the meaning. So what does it mean? And this is not captured by position always. This should come up naturally. That is, you can say that. Okay, so now, yeah, you can say that. Okay, now coming back before I talk about it. So what they're doing is that they are. So okay, no, let me talk about it. So let's say king minus. Let's say from the word king, you remove the queen. That means you remove the common thing between king and queen from the king word. Okay. So if king in a set and this is queen, so you remove this part. Then you only stay in this part. And after that, if I add, let's say, a woman, what will be that? Or let me make it better, in a better way. Let's say king minus dash is same as queen minus woman. So what will be this? What do you think?
Man.
Man.
So why? Because the relationship between king and man is same relationship between queen and woman, right? This relationship cannot be captured by just position, right? Do you understand what it makes sense? What I mean? So this is meaning. This is called distributional semantics, and this is done. I forgot the name of the person who did it. I'm sorry, but essentially, this to have so statistical semantics is nothing but a word is characterized. The mathematical expression of a word is characterized by the company of the word it keeps. That means the position. And linguistic terms with similar distributions have similar meanings. It means two terms, if they are similar, they have similar meaning, should be together. That means king and man should be together. And not only that, the distance between king and man should be same as the distance between queen and woman. This mathematical distance should be constant, similar, at least. Then you can like think about it like that. So therefore, the first step is to represent a word or a token as a vector, a d-dimensional vector. Okay. And then this, based on these vectors, we will do this positional stuff and the meaning, linguistic meaning stuff. Okay. But this is the most important thing. Did you understand, guys? Did you understand these two things? What we mean by position and what we mean by meaning. The statistical semantics and distributional semantics. What do they mean? Do you understand this, guys? Yes or no? Can I get a yes or no? Or you want me to explain once again? Okay,
Yes.
Rupoli has said yes, Hindal has said yes. Preeti has said yes, Laki has said yes, Shurajit has said yes. What about others? Rohini has said yes. Mrityunjay has said yes. Great. Konishko, are you understanding? Shanjana? Garge has said yes. Superb. Trishna just joined. I am not sure if Trishna is understanding. Okay, great. Thank you guys for your interaction. Okay. So again, words have two aspects. One is the positional information, the statistical semantics, and the distributional semantics, the meaning of the word. Okay. So now, as I've said, that a word is represented as a vector. A word represented as a vector makes sense, right? You all understood. So what is represented a vector? Like a king is a vector, queen is a vector, you can see. So what we mean that king minus queen is same as man minus woman, right? Because we are removing like the common part of it. So if we remove the queen and king in intersection, common part from the king is same as the man and woman, because at the end the royal thing is gone. I hope you understand. Like king minus queen is nothing but man minus woman, right? That's what we mean. And okay, so naturally the thing is that how do we measure that? So what we are saying is that a word is nothing but a vector, and if two words have same meaning, their distance should be small. Okay, so how do we measure the distance between two vectors? We define it by something called cosine similarity. Okay, if this is a fruit, this is an orange, and this is an apple, we measure the distance. So we have these vectors. If you remember here, we have these vectors numbers, and they should be, the distance should be same. Distance should be small. So how do we measure it? We can measure with an MSE, but no, we don't want to measure with the MSE, because the thing is that we want to measure how much angle they are close by, because we can have like two long, like one is short and one is long. Okay, you can see it's long, but it may be long because of various reasons, right? It may be long because of various reasons. Maybe because of various reasons. Okay, though, but we want them, they are close together, the angle is close by, they are holding the same angle from the x-axis, and that means we want to understand the angle, and we want to understand the angle theta. Okay, good. But if we take theta, it can be 0 to 360 degree, so we want to reduce it to something -1 and 1. Like when they are opposite, when they are far away, we want it to be negative, and they are close by, we want it to be positive, and that's why the cosine is coming. Okay, because if you draw the graph of cosine, it's this. If it's close, it's positive. If it's far, if it's negative, right? This is a cosine graph from 0 to pi. And again, it comes back, right? So, got it, guys? And we are taking 0 to pi because that's where the bijection is. But all of you understood this, guys? Why cosine we are taking? Because we want to get it between -1 and 1. Negative means far and 1 means close. Got it, guys? So a word is represented by a vector, and the relationship between two words is represented by this cosine similarity, cos of the angle between those two vectors. Right? All of you got it? Yes or no? These are all fundamental concepts, one step at a time. Can you say yes? I want more yes, because yeah, I know it's hard for you, but
Yes, yes, yes.
good. All of you got it, guys? Any questions? Anything I can help you out with? Because I wanted to ask questions to me, because I really enjoyed the discussion with you guys. You see, I really love when the students naturally discovers themselves, because the students have an understanding the way education system is in India and most of the places actually, is that it seems like the teacher is actually doing the teaching, but the whole idea should be the students actually knows the subject. We have to get it out of the student system and mind. And I really love and enjoy when the students can actually do it and then connect, and that's where they feel that they can also do it. They do not feel students anymore, they feel that they can also do something more. Okay, so now this is an idea in practice, so I wanted to actually verify that whether it's actually true or not. So what I did is I took BERT, is a pre-trained model, and I wanted to see that, hey, okay, this, you guys are talking about so much theory, did actually, like, after, so what they did is that they trained on the whole text like this, and naturally each word came out to be a vector. So I wanted to see that what you're telling, is it actually true? So I did this whole code and stuff, and you can see I defined cosine similarity. I took the embedding, that is a vector of each token, or here you can say word, and then I said that I wanted to see that what are the nearest tokens to certain word, and I did the token of king minus man plus woman. Okay, and this should be queen, right? And you can see that first king is coming and the next is queen, and not only queen, if you see the next one is also woman. So what it's coming out are princess, that was never there. Like, we didn't think about this. So what does it mean? It's actually learning the meaning. Do you see the point? Because you see how many places there will be a princess always, right? Present. So yeah, or this is the beauty of it, what I'm saying. Queen, princess. So this royal thing is coming out, which is present in man, not present in man and woman, but present in king. So this, you see that king, the relationship between king, just like the relationship between fruit, like apple, mango were fruit, and apple and headphones were the company. Similarly, the relationship between king, queen, and princess, this is all coding, okay? This is all trained on large datasets. It's nothing but royal family, right? The royal family aspect. So you cannot, you are not hard coding into the model. The model is learning it, and that's exactly what we want. That means GPT or all these models actually also boiling in or bringing in, I'm sorry, the meaning, the distributional semantics of words. Okay, all of you understand the beauty of it. So they are also positional encoding. That's why it's giving out good output, but it's also understanding the relationships, the fundamental relationships. Okay, all of you got it, guys? Yes or no? So I want to test it out. That, so think about a method. This is an exercise for you guys. That king, queen, and princess, what is the kind of relationship that the model is learning? Is it royal? So how do you find it? Describe a method to find the royal. Is there connection royal? Is that where the code connection is from? Think about it, guys. Okay, can you do some coding? So you can take this code and try to do it, experiment yourself. That is royal the connection, the common connection between these words. All of you got it, guys? This one, I'm sure you have got it because we already discussed it. Now we have understood that what we need to do. Okay, now we will discuss how we are doing it. Okay, initially we understood why we need to do it, why we need to understand the mathematics. Okay, because it's not there. Now we understood what we need to understand in the mathematics. Okay, that is distributional semantics and positional semantics, like statistical semantics. That position and meaning. Like distribution is meaning, statistical semantics is position. Now the next question is, last question is how. So, and we will see that the whole attention, that attention is all you need, that paper. It's where the secret lies. It encodes both. Okay. And that's what we are going to learn now. And you will learn attention. You will learn attention in the future classes. But you will not learn attention in the way, in the context of this distributional semantics and statistical semantics, because that is not general attention. So it's my duty to teach you what is attention with respect to language, and it actually encodes the meaning that we all discussed together, we all discovered together today. Okay, so let's understand this. Now we're going to discuss how we are actually doing it, encoding those two fundamental information. Okay, so now let's understand. So let's take the sentence. Harrington taught at Harvard University and the National War College. Let's understand a bit more about the positional stuff and the meaning stuff also. So here you see that Harrington is related to both Harvard and also National War College, rather the college. Now what I mean is this, that if you, okay, so let's take this picture, this plushy toy, and let's say you cover this part of it. Okay, let's say this is masked. Now you cannot really predict. You can predict about its toes, right? If I also cover its toes, you can say yes, the body color is blue and white, so it should be blue and white, and yes, it's blue and white. You have understood, but you cannot probably predict its fit because it has 3 toes. Okay, it has 3 toes, so you cannot probably predict its fit because you may have thought, I mean, you don't know, you probably think it's penguin and multiple things it can be. You can probably predict 4 toes, you do not know. So, but you know it's the color, so you know some information. But if I close one side of the face of this penguin, let's say, you can actually predict the next side pretty well, right? You can actually predict the next side pretty well. So what I'm saying is that an image, so if you're actually seeing an image, this whole thing is an image, right? What I'm saying is that image has more local connection. Okay, locality wise. Like if you have a boat in a sea, and if you close a part of the sea or a part of the like a boat and the sea, you can actually predict that around is blue because it's blue, it's in the sea. Similarly here. So image information is local. It's mostly local. That's why convolutions that you will learn play a very big role. Okay. But in language, it can be like, you can see Harrington can be related to the word at the entire end. Let's say it's 1,000 word, like not 1,000, but what I'm saying is that a word can be related to a really end of it. Okay, even if it's a large word. Like you can make somehow the language in such a way that the National War College, you can make this sentence huge, so this National War College really comes at the end. Okay. So you can like say Harrington taught at Harvard University. He's a really good teacher. He has done his PhD, master's, bachelor's from this. His thesis is this, and you can make it really large. And last at the end, you can write, he also teaches at National War College. Now you have 100 words, and now at the end, Harrington is related to the National War College. It can never happen, almost never happen in image. Not almost, but yeah, in real cases it will not happen. But in language it can happen, right? So what I'm trying to tell you is that it is long context length. You need global relationship, the position. So what I'm saying, this, as I said, what has two aspects, meaning and position. The position should be global in nature. Like it should do right at once, not like wait for it. And that's why CNN and RNN and LSTM cannot solve this problem. That's why attention could only solve this problem in 2017. Okay, because it does a global attention right at one layer, and we will discuss this in details. So we need global attention. We need global context of the entire sentence right at once. All of you got it, guys? This is very important. This global thing is very important. Global context. All of you got it? Can you say yes or no? Yeah. Let me not ask you for every time to say yes or no. When you say, like, can you understand? Did you understand? You can say just yes. That will be helpful. Okay. Anyone who didn't understand or have some questions? Global context. Okay. Okay. So now we will now take a bit of our time to understand that how attention actually solves this aspect, and this will take some time. So let's understand. So let's actually duplicate this page. So I've given the links out here so you can check it out. The links I will share this PDF with you guys. So actually I will post this PDF on LinkedIn tomorrow, and you can download it from there. Okay, I will share my LinkedIn ID so that way you can also get in touch with me if you're interested. So let's take this simple thing. I love tennis. Okay, so we already understood that each word is a vector. Here's a 4-dimensional vector of numbers. So each word is a vector. We already set up this. Right? Each word is a vector. R to the power 4. Now, so this input embeddings is nothing but number of words n cross 4 here. Right? Yeah, I'm writing the dimensions because it's super important to know the dimensions. Understand it very carefully. Okay, so all of you understood this, guys. This may be a little bit difficult, so I will ask yes more often, and I want you to say yes because I cannot move ahead. So did you understand this? That this is a n cross 4 matrix where n, the number of rows, is the number of words, and 4, the number of columns, is the dimension of each word. Did you understand this? Yes or no? Can you quickly say yes? Yes. Good. I will go to the next step. Good.
Yes, sir.
Okay. So now what we want is that this dimension can be really, really high. Like here it's 4, but it can be 512 or more, right? But we want to, for the computational aspect, because the larger the dimension is, the more computation it will take. So what we want is to reduce it to a different dimension. Okay. So, or change it to a different dimension, let's say 3 dimension, dimension 3. So our output is, our goal is this. We want to change it from 4 dimension to 3 dimension here. So yeah, 3 dimension here in all of them. So now you can think that why there are three such, why there are three such things. One is called query, one is called key, and one is called value. Why are three such things? The reason is simple. The reason is how we search. Okay, simple idea. Because we want to understand that we're going to encode the relationship between them, right? We want to encode the relationships between them. So imagine that you are building a Google search. Okay, you're building a Google search, or a simple thing. Let's say you have a book. Your professor has given you a LaTeX notes, typed notes. Okay, and let's take this hypothetical scenario. Your professor has given you a typed notes, and you have a demo test paper, mock paper for your semester examination. And there is a word, let's say something called Markov chain, let's say. And you've forgotten the meaning of that word. Okay. And there is no content page, like table of content page. You've forgotten the meaning of the word. And you want to search the meaning of the word in that book, right? In that type notes. So what do you do? Any idea? Anyone who wants to share? I'm sharing a problem now. Any ideas? How do you search that? What did you do before GPT? Google didn't offer this service, right? Google didn't offer this service of you can upload a book and then search, right? So how did you do? Any idea? Simple problem, guys. Unmute yourself.
Just put in the search string in the search bar that comes with a PDF or a document.
Very good. So very good, exactly. So we have a search bar, right? And we put in our query, that Markov chain, and then it goes and search in the text. So let's understand it carefully. So we have a search bar, we put in the query, and then it goes in query and goes into text, and there's a text, let's say, and the text has, let's say, 3 words, let's, for example, and it tries to see that query matches with this or not. And if the match is high, then they return the search. Right? Yes or no, guys? Yes or no? Did you understand this? So if a query, you send in the query, and then there are different keys, let's say key 1, like each of the words, okay? Key 1, key 2, these are, and then it searches there, and it shares you that where it is there with high chance. Okay. But this is just like exact word. But let's say I want to search Markov chain, or let's say I want to search apple, and I'm okay with any other fruit. So I want to also give me mango. Then this is much more important, right? This is how it's, you want to search apple, and it can also give mango. You're okay with any fruit. So there is an input query from the same text, and there's a key search, right? You want to find the relationship between two. There's a key, and you want to match the key in query. All of you got it, guys? Yes or no? Did you understand this? Yes or no? Yes? Any questions? This is very important, guys. So please tell me if you don't understand. Can you give yes or no? Did you understand? All good? Okay, I will assume it. So you have a key and query, and the match, and there's a match. So we are doing the same thing here. We will come to the value later on. Okay, we will tell, because you can see the value is kind of outside the loop here. The value is kind of outside the loop here. So in this case, we want, so essentially the goal of the embedding, a new embeddings that we are creating here, this, as it says, it needs to be context aware embeddings. Here the embeddings are just embeddings like as it is. Now we want the embeddings to be context aware, that how the relationships, how this encodes the relationships between each one of them. Okay, this is where the meaning comes in, because the meaning comes in by interrelationships, right? So here the meanings, the embeddings are updated based on the meanings. Okay, this just don't have any meanings now when they're inputted, but these have now meanings among them. That's how the embedding is there. Okay, so how it is doing? So it is passing through a learnable set of parameters, because we don't know what the query, what the embedding should be. So we develop what the perfect query key vectors are. So these are kind of, again, a meaning of the word. So they're creating three different queries for three different words. Okay, so you can say something like this. So let me explain it in a better way. So you have word 1, word 2, word 3. Okay, these are embeddings. So let's, and this are changed. This is changed to query 1, query 2, query 3. This is also changed to key 1, key 2, and key 3. These are what you are seeing here. So now this is Q, this is K. So what we're going to do now is we want interrelationships, right? So we kind of do the dot product of it. We kind of capture the, we kind of calculate the cosine similarity of it, because you can see cosine similarity is nothing but dot product, normalized dot product. So we capture the cosine similarity. Now understand it very carefully. So what we want, what is dot product of Q1? These are vectors, right? Just three-dimensional vectors. So these are R3, three-dimensional vectors. So this is Q1, this is Q2, and this is Q3. And this is K1, the Q1. Because what we want relationship between each pair of words. Naturally, this gives a 3x3 matrix, where the ijth pair is nothing but the relationship between jth and the ith word. And how it is done? It's simple. Q dot K transpose. So let's do this bit of mathematics here. Simple mathematics. So if this Q3, 3 rows, and K transpose becomes what? K transpose are 3 rows transpose, that means those are becomes the columns. So this is n words and 3 dimensions. Now K transpose was n cross 3, it now becomes 3 cross n. That means 3 rows, n dimensions. Sorry, 3 columns. That is K1 transpose, K2 transpose, and K3 transpose. Now, when you multiply this 3 cross n now, what do you get? The first one will be q1 dot product with k1. The second, this one will q1 dot product with k2. This will be q1 dot product with k3. So any ij there will be qi dot product with kj. Right? So what this is what this matrix is doing. It's the attention score. That means the attention between each pair of words. Why? Because each pair of words have relationship. Each pair of words may have a relationship. We don't know where the relationship lies, right? So in this attention map, let's say Harrington will have high relationship with Harvard University and National War College, let's say. If there's are words, high relationship, let's say this one. Just like, yeah, high relationship, not this one. Let's say, yeah. Because the relationship with, so KII is nothing but the relationship between with itself. It will of course be high, right? Naturally. Two words or relationship is naturally high. And of course, it's not cosine similarity, but yeah, it's high. But yeah, you can see 0.2, which means the relationship between love and tennis is more. So this is where the meaning comes in. This is not just position, but this is where the meaning, because the apple and mango will have a high attention score with time when it's trained more and more. This attention is there for the fundamental of the meaning, the distributional semantics. Okay? Distributional semantics. All of you understood this, guys? This is very important. Did you understand this? Yes or no? Any questions?
I just have one confusion. Like when you are saying that Harrington is going to have a close relationship between the names of the two universities, why is that going to happen? Because they are not similar in meaning. I mean, they are just different names. Harrington is the name of a person, and the other two are names of two universities or institutions. So, why would there be a greater similarity between
That's a great question. So when I say meaning, the meaning not only comes from so just give me a minute. Yeah. So the meaning, what I'm saying, when this attention score not only just stores the meaning, but you can say both the meaning plus how many times they're occurring together. That a person, so you don't think in Harrington and Harvard, but a person, a teacher, let's say Harrington is associated with a teacher. Let's say there was a word that Harrington and teacher associated. Now teacher and college associated, and college and university, Harvard University associated. This is the relationship. Makes sense?
Okay, got it.
So it's like it cannot be just direct, but it can be hierarchical relationship. But that must show up here. Make sense? Thank you for the beautiful question, Ritik. Any other questions? All of you understood this, guys? Okay. Yeah, great questions means that good questions means the person is understanding. So thank you, Ritik. So this attention score is therefore the relationship between individual words, the word pairs, the keys and the values. Okay. Now, the attention score is there, but we want it to be inside this new value, so that, because you see that first time, so you can think it like this. Let's say you do it for the first time. As exactly what Riti has mentioned. Let me take that example. That Harrington is not related to Harvard University like right away in meaning word. But if you train more, what happens is that more and more words come up. Okay. And Harrington association with teacher and teacher association with college and this college association with Harvard, this four doesn't happen right away in this one attention. It can happen only when the word embeddings contain the previous attention context aware information. Like what is happening is that in this, okay, so let me give a very simple example. This is so exciting. So initially, let's say, let's take this example. Initially, let's say this was Harrington and this was Harvard, let's say. But we want this to be close by. So we want the new vectors. This is the initial input embeddings. We want the new vectors to be like this, at least. That means they are becoming close by. The angle is reducing. We want it to be better. We want it to be more close by, right? That's the whole idea. We need that. And that's why we need updated embeddings, because if this doesn't happen, let's say when we train with something else, so this is what is happening, understand, guys. So Riti, thank you for this beautiful question again. So in some other training, what will happen is, let's say in the 3D, okay, Harrington will come close to teacher. Let's say it will be θ1. In some other training, teacher will be coming close. In some other data set training, teacher will be coming close to university. And then some other training, teacher will be, university will be coming close to Harvard, right? So what we want is each of this training, each process, as we move forward, we want the embeddings to be close by, because if they are not close by, they will not learn this common relationship, right? So we want the embeddings to update based on the meaning. That means their closeness has increased. Makes sense, guys? Makes sense? So that's why we just do not need just the attention, but we also need the updated embedding so that their relationship closeness, the meaning actually is reflected in the new embeddings. Okay, guys? Did you get it? Yes or no? All of you?
Sir, I have one query.
Yes, please.
Okay, so in this very small example that we are looking here, I love tennis. So if I understand correctly, for the first cycle, we are calculating the association score between I love, I tennis, then
Exactly.
love, I. Okay.
Exactly.
So after the first iteration, we get high scores between I love, but not between I tennis.
Right,
So,
you can say that.
Okay, so then this high embedding goes to the second cycle, and now we can find association between I love as a single unit and then tennis as a separate unit. Rather
Right,
than,
you can say that.
is this
So
what is
yeah,
happening?
yeah, it's kind of what is happening. You're right, but there's more to it, because understand it's happening over multiple data iterations, right? Different datas are coming in. So you are now constrained to think about just I love tennis, but let's say somewhere it came, like there was a word like Rupali plays cricket. Okay, so and then somewhere else like Riti plays golf, and somewhere there's a sentence like I am Riti. Okay, so what is happening in this in different cases is I tennis, I Riti, Rupali cricket, Riti golf. This all come together, and it turns out that I is related to Riti and I also related to Rupali, and tennis is related to golf and tennis is also related to cricket. So all this relationship come up. So when you're saying this, it's not only happening across this sentence, it's also happening across multiple other sentences that are there in each and every training. So how this gets updated? This can only get updated if the individual vectors get updated. And these vectors are get updated only by the angle, the relationship in angle, the meaning angle between two words. Okay, Rupali?
Yes, yes.
So it is not just this sentence, it's just multiple sentences over and over again. So what we need, so you're right, progressively it's learning the relationship between I love tennis, but it's also using this relationship in the future. when it's others or other words are being trained into the system, other words from the vocabulary are coming into the system, this embeddings are updated, which contains these individual relationships. Okay. All of you clear with this? I will just call out the names once because this is very important and to contain.
Yes.
And in fact, this is the most important slide of all. Gargi, Konishko, Laki, Mrityunjoy, Rohini, Shanjana, Shupriyo, Suraj is
Yes,
already
sir.
said. Okay.
Yes, sir.
Shagato, Krishna. Okay. Good. Yeah. Okay. So now we are not solved here. We are not here yet. We understood how the attention comes in. What we have not understood that how it's updated. So what is updated? So based on this attention, what we know that. So what does this say? So 0.7 says the relationship of I with I. 0.2 says the relationship. So let's go here now. Yeah. 0.7 says the relationship with I. Relationship 2 says 0.2 says the relationship with I with love. And this says I with tennis. So how we are getting this new I updating from this? So we are learning some vectors, some embedding here, some low dimensional embedding. Okay. And understand this. So understand how this new embedding is formed. Understand the vector representation of it. So this is attention n cross n, and there is this old embedding coming in, and the new embeddings comes out. So this is n cross n and this is n cross k, and naturally the output will be n cross k. So how this first vector comes in? First vector is 1 cross k. So this one is being multiplied with this one individually. Okay. Or just give me a minute. Times p. Yeah, s is done. P. So what is happening here is, understand this very carefully. This. So we have to write the linear algebra properly, carefully. Okay. So we have the attention here. N cross n. And we have the n cross k here. So you can say that these new vectors are nothing but this weighted combinations of these vectors. Okay. So these new vectors are coming out in the weighted combination of each of these vectors. That means these weights are put into the system. And hence the weight means the dot products, and hence the vector adjusts with itself, right? The weights are put in because you can see, observe it's, so you can see it's divided by root over dk, and there's a softmax which is nothing but making it into a probability distribution. So the weights are adding into the system. Okay, the weights are being added into the system. All of you got it, guys? It's kind of the weighted combination of the previous vectors. Got it? Yes? No? So it now encodes the information of the relationship between them. Okay. Yeah. So let me just move it here. Okay, so now there is something more. There is a positional encoding. So the positional encoding is what? The most important aspect of. So let's say, as of what we did now, whether I say I love tennis, I tennis love I, all these things are same, right? Because this attention map can be changed, right? You can rechange this and this attention map will change. You can rechange the ordering, the attention map will accordingly change, okay? And hence the embeddings will change. So this is only about meaning, the relationship, the meaning. But there needs to be something about encoding, that I should come before love. The subject ideally in active tense should come before the verb, right? So
Sorry to interrupt you. Can you go back a little prior on the prior slides where the softmax was mentioned? Yeah, over here, I just want to know this 3 by 3 matrix. This is the result of the softmax
yeah.
function, and you just now said that it is transfer the softmax. This transfers it into a probability distribution.
Yes.
But if it is a probability distribution, then
Across each row.
okay, then it's okay. Because if it is for the entire, then it doesn't add up to 1. That's why I
Oh
was
yeah, across each row. So you can say that, okay, very good point again. So essentially I goes to, it's kind of, we can say what is the chance that I is related to love, and what is the chance I is related to I is related to I is related to love, and I is related to tennis. Okay, and when we have found out the probability, the I vector comes out to be some weighted average of it. Okay. So yeah, essentially it's kind of interesting. I goes to love, tennis, and I itself, and then it goes back to I. So it's not only, it's, we are not only capturing. So when I say the updated value of I, it not only captures how I goes to love, but also captures how love goes to I. Okay, that's how the vector is created. So it's sees that how I is changing to love and how I is changing related to new words, and those related to new words are also, like, new words are related to I. Both these are captured. Both the sequences are captured. So yeah, that's why, like, okay, so if you know Markov chain, guys, so this is, so essentially you can prove. So there is a recent paper by Google, I will show you towards the end, which says that these are nothing but Markov chain. The whole attention mechanism is nothing but a Markov chain. And in fact, the whole thing that started this distributional semantics are nothing but Markov chain. Okay, that's the beauty. We are coming around circle, and we will talk about why others couldn't solve it. Other methods couldn't solve it. But is your doubt clear, Ritik? I hope it's clear.
Yeah, yes.
Okay, thank you. Any other questions?
So here basically every word is being represented as a weighted linear sum of the other words in the text plus global knowledge. Am I correct?
Yeah, exactly.
Okay.
So it's okay. So exact mathematics, I am not doing the exact mathematics. I wish I had time. This will exact mathematics will be done in the attention thing. Okay. So I have also an exact mathematics discussion out there in one of my videos on YouTube. You can check that. I will send that to you. But yeah, because I have another 20 minutes left. Okay, so I don't know. I have a few more points to talk about. Okay, so you will see essentially so essentially a single word is going to other words. Let's say A, B, C. This captures probabilities of the words going to I, B, and C. But it also has another thing, that words coming to I, B, and C, like each of those words coming back to W. Both the information are encoded. Like, for example, after I am is coming, but after am I is not coming. So it's asymmetric, right? So both the information should be coded here in this vector. So when I say vector is weighted average of both the relation, both the relationship. Okay. Both the information should be there. Rupali, does it make sense?
Okay.
Yeah, the exact mathematics, yeah, we don't have time today, but you can read online or you can reach out to me on LinkedIn. I will share some resources, okay? For you to understand. Okay, so now the positional encoding. So positional encoding is, as I said, it encodes the position of each vector. So what is happening is that each word has its unique position in the entire sentence. 1, 2, 3, 4. But we want that position. So this is the embedding. And remember, the embedding contains the meaning of the vector. This is the best way to remember it. The embeddings contains the meaning of the vector word, and the position contains the position. And we want it to be simple. We always want it to be linear, okay? Because that's how deep learning works. So what we want to learn is get is a different positional embedding that contains the so essentially for this position 1 we will have a vector, and that's what positional embedding gives. And it is done with a unique interesting thing of sine and cosine. So each word has one positional embedding. Each word has one positional embedding because of its embedding, because of the position. Okay, so the word Harrington or like I love tennis has different positional embedding of tennis than tennis love I, right? So, and I love tennis will come more, hence that positional encoding will be used more in training and hence will be preferred by the model. So now the main question is that I hope all of you understood this, that what positional encoding does is essentially solve the positional stuff, that it's a statistical semantic stuff. This is where we know the position is like the positional relationship. So you see that both the meaning and the positional relationship is getting into this final vector. I love tennis. This is where we start. So this contains both the positional relationship. So this matrix attention contains both the combined information of position, the relationship of position and meaning of both words combined. That's why it's so powerful. Okay, the attention is so powerful. So all of you understood this positional embedding, guys? Like the base understanding of it, there is something more too. Yeah, again, the asymmetric, as I told you. Time love, I love tennis, and tennis love I are different. So it's asymmetric. Before I come to go to the next slide, I want to understand if you understood or not. Can you give a yes or no if you understood or not? Positional encoding as of now. Okay. Rohini said yes, Kanishka said yes, Riti said yes, Lucky said yes, Mrityunjay said yes.
Yes.
Okay, thank you, Indol. Rupali said yes, good. Thank you. Gargi said yes, great. Shurjit said yes, good, super. Glad to know you're all following. Thank you, Angana too. Okay, so now the final aspect is the linearity of positional encoding. And this is written in just a small line in the attention is all you need paper. That for any fixed offset of k, the positional encoding of like position plus k is represented as a linear function of position. That means the positional encoding vector at p plus k position is nothing but a t times a linear representation, a linear matrix times the old positional encoding. That just encoding of the position. Now, why it is important? This is something you have to understand. The importance is very simple. Let's say you have a big text, let's have 100 words. And in one of the text, the positional encoding of I love tennis is in the first 3 words. In another text, it can be 100, 101, and 103rd word. Right? Another text can be 50, 51, 52. Right? So the position, so the relationship between I and tennis or love and tennis, all these words should not be dependent on the position itself. So it should be independent of the position. So that's what we call relative positions. So this matrix is therefore learning the relative position. That means that the relationship between I love and tennis, when it is in the first part of the sentence, when you're training, is same as the relationship between when it is in the middle of the sentence or end of the sentence, because the relationship is the same. If we had different positional encodings and this property was not there, it would learn more position related properties, which is not important, and there would be overfitting in machine learning language. So therefore, this is a really good domain enriched way to actually encode the relationship here. Got it, guys? This is so beautiful, right? Got it? So beautifully done. Did you understand this? All of you? Thank you. This is so fundamental. This is very important. And this is happening. This relationship is coming out because sine and cosine have periodic properties. Because of the, or rather, not sine and cosine, yeah. Because of the relationship, it essentially turns out, if you read the proof of it, there is a proof of it. I'm not going to it. But if you read the proof of it, you will see that it's like it's sine of p plus k is sine of p times sine cos of k plus cos of p times sine of k, right? And the sine p and cos p is already there in the position encoding and the previous position, that is pi 1, pi 2. So it's nothing but sine k and cos k added linearly to it. Okay. And we get this tridiagonal matrix. Beautiful. Again, beautiful. Okay. So the final thing, that why convolution and RNN LSTM cannot solve this. Okay. Why convolution and RNN LSTM cannot solve this? The answer is again beautiful. So in convolution, and you will learn probably about convolution in RNN LSTM later on. But the convolution is, if you observe, so all of you, anyone who doesn't know about convolution, guys? Anyone? Can you raise your hand or say, yes, I will explain it else? Yeah, I do not expect you to know. But since time is short, that's why I'm asking you. Okay, fine, I will explain it.
I don't know.
Okay. Don't worry, I will explain it. I do not expect you to know. Don't worry. So it's like kind of, all of you know about moving average? Do you know about moving average? Hear the word moving average anytime? Rupoli and others. Hindol. Rupoli,
Yes,
do you
sir.
know about moving average? Okay. So essentially, it's kind of moving average, like not moving, yeah, weighted moving average. So let's say there is a word like 0.2, 0.3, 0.1, and 0.5, and you want to take a moving average of 3. So you do 1 by 3, 1 by 3, 1 by 3. And what do you do? To get the moving average, you first multiply with this, this, and this, and then add it, right? So that operation of multiplying this and then adding it, so you can say sum and dot product. You can say like this. First, there is a dot product between this and this, and then there is a sum happening. So that is the one. So this two interact to become one of this. And then again, this shifts, and then this happens on this one and this one. First, it happened on this one. That's why you got this. Okay, let me try out. New. So this connects with first this one to get this one. Now the same thing will connect to now the next one, the green one, to get the green one. The same action. So this is what convolution is all about. It's a moving average. So what happens is that when you do convolution, it extracts specific features out of it. So for example, moving average in stock market data extract the features of how the trend is going in one-dimensional signal. In images, it's the same. Similarly, in language also it can happen. But now let's say if it was another word, another one, let's say it's 0.6 here, and let's say you now do purple or you now do yellow. It will be this now, and there will be a yellow one. So this we get 3. Now we again do this on this. So then there'll be this 3 will turn out to be one number, right? Because if you do with this, this will turn out to be one number. So this was layer 1. So you can now observe this. If you do convolution on the first channel, in the first layer it will reduce it, because this 3 are coming out to be this single number. In the next layer, this 3 are coming out to be this number. But understand how the attention is there. This one now goes to this 3, and each of these 3 now goes to this one, because this contains now this, right? This information contains is this. That means as you go deep into the layer, it's called the receptive field. That means this encodes the information of a much larger area. Similarly, this encodes the information of the entire thing, the red thing. So, did you understand this, guys? All of you? Rupali, Ruhindal, whoever asked. Did you understand?
Yes.
Any other questions? Okay. So, what I mean is that with increasing number of layers, the receptive field increases, but not at one time. When we said language, that's why the reason we said that. Now you can calculate that to get the full receptive field, we need, let's say, certain number of layers. Let's say 10 layers. That means we get the entire global context in 10 layers. But that will not help. That will make it very slow for this whole global context of the language. Language, it cannot happen because the global context is not there. Okay, this is not the case in stock market data, because in stock market data we do not need the global context. Why? Because what happened 50 years ago doesn't matter, or let's say what happened even 1 year ago doesn't matter, even what happened 1 month ago doesn't matter. That's why in stock market in time series we have something called Markov property when we model it using stochastic processes. Okay, but in language we cannot do that. In language, therefore, we need attention. We need attention because of the global context. And the reason attention is so successful is because it takes global context one at a time, and it's just matrix multiplication. Okay, since it's matrix multiplication, it takes global context each layer instantly. And this matrix multiplication can be, as I have shown, it's nothing but matrix multiplication, right? We have shown it here, we've proven it here step by step using the whole process. The whole attention is nothing but a matrix multiplication. The updated encodings, the context of embedding is nothing but matrix multiplication. And this is essentially, this matrix multiplication is nothing but parallel computation using GPU. That's why using GPU is very important. Okay, GPU solves it by parallel computation. And you will learn, the CS students know it better than me. It's parallel computation happens in GPU, which is not possible always in CPU, this parallel processing. It's in order of, let's say, two vectors multiplication dot product, let's say, takes t time. A matrix also will take t time multiplication because of the parallel computation in GPU. If it is not in GPU, it's in CPU, then it will take n times n if there are n vectors out there, n squared times. Okay, it's a sequential process. But it's in the parallel computation, it will take t times, like just t time. So it will be n squared times t times for, if you do it sequentially, 2 vectors at a time. Or rather, yeah, order of n squared. Actually, it will be n choose 2. You can say like that, n choose 2. But that will be n squared minus n by 2, but it's in the order of n squared, right? So, but yeah, so what I'm saying, but in that case, it will be order of t. So it will be actually order of 1, constant. I'm just giving a simple example. That's how parallel computation works. So it's faster. And matrix multiplication helps us in that. Okay. So like parallel computation helps, matrix multiplication is done using those parallel computation using GPU. That's why GPU helps us. Again, in RNN and LSTM, it actually could solve in RNN and LSTM. It was sequential in mind. It's like sequential data. Okay, it sequentially updates itself, kind of like this. Here it happened layer wise. You can also say it happens layer wise here. Each of them actually called a layer. Okay, so this is the problem. This is the problem. and see, attention solves it. So if you got it, why attention is important. Again, connecting back to the first thing, global context is important in language. Got it, guys? Did you understand? Yes, why it does solve this, guys? Yes or no? Can you say yes or no? Any questions? Good. Okay. Now, a final thing, again, we will repeat it next day. So next day, we will be understanding the deep learning process. But I want to talk about something important, that how. So, okay, two things. I will talking about this again next day. But one important thing is that how the tokenization happens. And actually, it is not done word by word. If you go to this app, a tick tokenizer Versal app, we will see that it happens. It happens in different ways. One way is byte pair algorithm. So I will share resources with you. I already shared resources here. So go to these people. This, if you know Andrei Karpathy, he is my favorite, and Sebastian Rashka. So go to this YouTube profile. He has just 17 videos, but he has almost 1 million followers because of the depth of his lectures. I go there, and there is a very specific video called tokenization. Okay, and learn from it. You will understand what is the meaning of tokenization. But yeah, the whole goal of this crash course is to tune your mind into the thinking style, into the fundamentals of this why and how and what. Okay, and I'm sure, I'm hopeful, and you will tell me at the end whether I have done the justice to that statement or not. So there is tokenization, and the final thing is that how the entire data is changed into training and testing. Okay, so what is done is this. What is done is the data is separated into chunks, okay, of trend test, chunks of trend test. So the whole data set is, let's say 100 words are taken out, and out of those 100 words, the first, so what, as I said, it's like time series, right? You're predicting the future. So the first 100 words is training, and the next 110 words is, or like first 90 words. So first random 100 words are taken out for the entire text, let's say, and the first 90 are for training, the next 10 words are for testing. And while inference, like while inferring this final word, so we will discuss this in details next day, okay? But while inferring the final word, we take actually the prediction. So for the first one, we predict this. For the next one, next two. So once we have predicted this, we append this and we predict the next token word. And we append this and predict the next word. That's how the next 10 words are coming up. Okay. We are using the best possible guess to get to the next word. So this is how the whole training and testing are distributed. So next day, what I will do on 23rd August, we will be talking about the entire GPT architecture, and we'll talk about how we have coded each one of this with a simple example. Okay. How the batching is done. We've also revised the deep learning process entire. I already made the slide, so we will see how the GPT is formed. We will see the mathematics of each one of the aspects of the attention mechanism, and we will see how it's trained. So we will learn how deep learning works also by this example. And I will not code this because this will take some time, but I will share the code with you. You can share it in your time, but I will explain what it means individually. Okay, and then I will discuss how we actually made this whole GPT architecture, like each class and component wise. Okay, that's what on 23rd August it will happen. Okay, but still I will share this with you, and I will start discussing. So I will share that the things I have discussed, and we will start discussing from day 2, that is the deep learning process, and the next onwards. Okay, we'll first revise what is deep learning. We'll discuss a bit about the whole process of optimization, because that's what we'll use in the coding, right? For example, this gradient descent is nothing but there in the solver in training code. In this step, optimizer dot backward step, these 2 steps, right? So we need to understand that. So thank you, guys. Any questions from your end? Any questions from your end, guys? I hope you have learned something new. Any questions from your end? Okay. So thank you for attending, guys, and I will share my LinkedIn profile. Just give me a minute. And I will post this notes tomorrow on LinkedIn. So if you're interested, you can download from there. So I will share I am sharing the link in the text box here. And if you have some questions that you do, if you're shy and you couldn't answer those questions now in live with me, feel free to reach out with me. I accept everyone's request. I do not reject anyone's request. So you will be able to talk with me after I accept a request. Okay. So thank you, guys, and all the best. See you on 23rd of August. Bye-bye. Absolutely.
Thank you, sir.
Thank you.
Bye.
Yeah, sure. Thank you all.